Hello, students. To explain endo and exo, we're going to review a little bit from last week, and we'll begin right here in the activator, which talks about exo and endothermic. Exo, think of it exit, heat leaving, and endo entering. Simple as that. But it requires you to think a little deeply when it comes to specific reactions. For example, in freezing, we have a substance going from a liquid where the molecules are a little bit further away to a solid where the molecules are much closer. And in the video, they talk about bonds, and this is indeed what happens is a bond will form as the molecules get closer together, and in that formation of bond, you release energy. Something to keep in mind here, this idea of something being cool is referring to the heat release, not temperature necessarily. During phase changes, temperatures stay constant where bonding is forming, and so the energy there is going not into making the molecules change their velocity, which is what a temperature change would do, but changing the bonding. So in melting, here we go from a solid, molecules close together, to liquid where they're a little further apart. That is a bond that's being broken, which requires energy, and that is endothermic. Boiling, you have liquid, molecules a little further away, now going even further away. So that bond is broken as well, requiring energy, endothermic. Condensing, which is the opposite of boiling, gas going to liquid, is a formation of a bond and would be a release. Moving on here to evaporation. Evaporation is a little more complicated. Evaporation is the spontaneous release of molecules from the surface of a basically liquid. And this is due to molecules moving at a faster speed that happen to get close to the surface and just fly off. What happens in that case is the faster molecules, which are therefore higher temperature, are removed. This would be what we call an open system. Those molecules removed, which are the faster ones, leave the slower ones behind, which are the lower temperature. And this process of evaporation is therefore exothermic, causing a release of energy. Think of when you're sweating and you get wet, right? That sweat evaporating cools you down. This is different from what we said earlier with boiling. Notice the phase changes are the same, but in boiling, this is an endothermic process, by the way, I described earlier, but here evaporation is not the same process. So just to be aware of the heat here is the the faster molecules that are leaving spontaneously and leaving the colder ones behind. Going down here to burning, I think that was pretty straight up. Exo, releasing heat. Explosions are just really a violent burning. It's not any different than a burning of a gasoline, just it's much quicker. And then a chemical cold pack is where, you've got an injured body getting cooled down. That is meaning the pack is absorbing heat from you. You're feeling that it is experienced by being cool. Here in this video, I know it went kind of fast, and I understand that can be kind of frustrating, and they throw in some chemical reactions like what is going on. But the basics here, we mentioned it already, that the exothermic is characterized by a rise in the temperature. The key here is that the thermometer is considered part of the surroundings. So if you think of it, you put it inside the fire here, the thermometer is going to get hot. Why is that? It's absorbing the heat from the fire. So the thermometer is experiencing, in a sense, an endothermic reaction. But I don't want you to get confused. We're referring to the reaction itself, which is exothermic. The thermometer, being part of the surroundings, would feel that heat coming in, and that's why we call it exothermic, meaning it's getting hot. The thermometer is getting hot. Absorbing energy, I think that's pretty straight up. That's your endothermic. Endothermic reactions are absorbing energy from the surroundings. And I just want to make a note that vinegar is ethanoic acid. They talk about it's baking soda and vinegar. That's an endothermic reaction. It gets cold. Exothermic reactions are, again, when you kind of the opposite of endo. It's releasing energy to the surroundings. Examples of that, pretty straight up: burning wood, freezing water, condensing steam. Why are melting and boiling, why are they considered endothermic, and freezing exo. I mentioned it earlier, and then it's in the video. It's all about the bonds and how that relates to the heat. Melting and boiling require an absorption of energy to break a bond, bond, and so solid to liquid would be solid to liquid is a breaking of a bond, and liquid to gas, breaking of a bond, and then freezing. Put a parenthesis in here, kind of editing as we go. Freezing and condensation are when you make a bond. As mentioned earlier. So, okay, what I would say with this next video, and I'm just going to keep rolling here. Please be free to pause or repeat what we say. I'm just kind of on a roll to get this in make the video relatively short. Anyway, for this next video, it's about that wonderful hippie Professor Dave. He's talking about specific heat. And that is something different from heat capacity. They're related, but specific heat is not heat. Heat is different. It's related, but it's not the same thing. Part of this unit is being very precise of the words we use, and there's new vocab words here, and this is one of them. So what is specific heat? It's the characteristic of a material, like the way density or hardness or color is. It's the amount of heat required to raise 1 gram of that substance 1 degree Celsius, or Kelvin. The unit of a Celsius degree is the same as a unit of Kelvin. The difference, of course, is where they set 0. 0 Celsius is where water freezes. 0 Kelvin is where all molecular motion stops. But the size of the degree is the same. Fahrenheit is a completely different scale. Their degree size is different, and we don't really use that in science. Fahrenheit is more in the engineering and in the United States. So I mention this because later in this answer key and even in the videos, they talk about Kelvin. They kind of throw it in there. They use the Kelvin scale just because there's no negative numbers. It's kind of an easier scale because of that. But the unit, the size of 1 degree Kelvin and the size of 1 degree Celsius are the same. Or I should say just Kelvin. It's not called degrees Kelvin. All right. Getting off topic a little bit. So in this next one, they ask about what is delta T. It's really just the change in temperature. Technically, it's the final temperature minus initial, which means you can get negative numbers. But to keep things simple, we're just not worrying about negative numbers right now, okay? In calorimetry, they talk about a hot piece of metal going into a coffee cup with water in it. The heat gained by the water is equal to the heat released or lost by the hot piece of metal. So we assume that there's no loss anywhere else. It's just from water. It's from the metal to the water. That's it. The problem here is, again, probably not enough time after the wonderful music, the elevator music. But basically, it's just plug and chug, as they say. The S is the specific heat. The mass here would be for whatever the specific heat was. In this case, it's the water's specific heat, the water's mass, and the water's change in temperature. I say this, it's maybe obvious, but when you have metal and water, sometimes these calculations can be confusing because you get mixed up. What's the mass? Is it the water's mass that I put in here? Is it the metal's mass? Well, it depends. Are you trying to find the heat of the water or the heat of the metal? If it's the heat of the water, then make sure you put the specific heat of the water. Make sure you put the mass of the water, and make sure you put the delta T of the water here too. I'm using D for delta. Here, the heat of the metal is equal to the heat of the water. We kind of talked about that earlier here in question 3, that the heats are equal. That's conservation of energy. And so we put that in and essentially solve for the specific heat. The S here is the unknown. M is the mass of the M here. I didn't put the MS delta T here. I just plugged them in. And this would be the mass of the metal, and then the change in temperature of the metal. Remember, the temperature of the metal started out pretty hot, so that's why it's 115. So we solve and we get a nice, lovely number there for the heat, which we could use maybe to identify what that metal was. In fact, the next activity talks about some specific heats of different materials. So the first is kind of a simple one between water and sand. And it's like, why is it that the sand feels hotter? Well, we got to assume a couple things. First, let's assume that the masses don't matter. You have a giant ocean, and the beach can be large, but the ocean is way bigger. So just keep it simple. It's because the sand doesn't need as much energy to heat up in order for its temperature to go up. So you can have the sun on the sand. It will get really hot, but the water barely raises the temperature very much. And it's because of this idea of heat, specific heat, that there's more energy required. The water requires more energy to increase its temperature. Different objects have different specific heat values. Okay, it's a property of material, and we recognize that. Again, this specific heat doesn't mean a specific amount of heat. In that, I have a specific amount of heat for this cup of hot cocoa or something like that. No, it's a property of the material, and it gets confusing because of the word specific. I understand, but just to be clear, specific heat is a property of matter, just like density, color, luster, things like that, hardness. A material with a high specific heat can absorb a great deal of thermal energy without changing its temperature very much. This is important. When you have a high specific heat, it means you need a lot of energy to raise the temperature just 1 degree. Water is a great example of this. In fact, I'd like to take a moment to look at that graph. We're talking about comparing water and sand. And so if we go there, hopefully this will come up quickly. You can see water has a nearly over 4,000 joules per kilogram. And notice here they're talking about Kelvin. Okay, 1 Kelvin. We talked about that. You could also say 1 degree Celsius, but they're making it Kelvin. Sand is maybe 750, and iron is less than 500. So clearly, water has a lot of heat capacity, specific heat, and that refers to that you need a lot of energy to increase or change the temperature of water. Now, it also goes the other way too. To cool water requires a lot of energy to be released. So this idea of heat needed to raise, it could also mean to lower, the temperature. That's important because heat can be gained, heat can be lost. And specific heat refers to both heat loss or heat gained. Then we get into specific heat of common materials. Okay, so this is comparing the highest to the lowest. And if I go back to that chart, if it can do so in a timely fashion, you can see just from here that water is pretty high and silver is pretty low on that table. And we put that in there as well. Sorry, I keep going to the wrong one. And then they ask about how does specific heat of covalent compare with metallic or non-covalent. And generally, there is an exception. Aluminum had a kind of a high number there, but generally speaking, the covalents have a higher specific heat. And you can get in. It's really about the bonding, the structure, the more properties, and it's fascinating. It's fascinating, but for now, we can see that the type of bond can determine the heat capacity. And I kind of use that term heat capacity, specific heat interchangeably, and I apologize for that if I could clean myself up a little bit. They're very similar in what they represent. We say specific heat because it refers to a specific amount, like 1 gram or 1 kilogram. Heat capacity, it doesn't matter the amount, but the idea that different amount of heat will cause different temperature changes, that phenomenon is the same for both heat capacity and specific heat. And it comes up with the next one, global warming. This video I thought was pretty cool with the balloons. So first of all, the 80 to 90% of the heat from global warming goes right into the oceans. So water is absorbing that heat for us. Because water can absorb 1,000 times more heat without really changing its temperature. It stays pretty cool. The reason for this is heat capacity. They talk about it. Heat capacity is that idea that you can absorb a lot of heat or release a lot of heat, but your temperature doesn't change. It kind of stays steady. So in the case of the balloon with air, it popped really quickly. Its temperature increased very fast. And so that meant that the air had a low heat capacity. It didn't require a lot of energy for its temperature to increase really, really quickly. So now when you put the water in there, in that case, the temperature increased very slowly. It took a lot of energy for that water to heat up. Now, I would also like to add that there was a lot more mass there. The water had a lot more mass than the air. The air there wasn't a lot. So there's that part that, because you can just simply have a lot of stuff and it's going to take a lot more energy to heat up. But even so, even if we had equal amounts of mass of air and water, the water would still have required a lot more energy to increase its temperature to pop, to break. And then two things to reduce global warming. I've got to say, they mentioned it kind of obvious: turn off lights, drive less, walk. But I don't know if you noticed in the beginning, and I have to mention this, is eat less meat. Okay, it's one of the chief principal contributions to global warming is the fossil fuels and the agricultural business that supports meat. There was some cows in the beginning of the picture there that would support that. All right, moving on to the lab. Notice that in this case, I think it was pretty obvious that the soil increased its temperature and cooled very quickly. Let me see if I can find that here. I think that there it is. So notice the soil quickly going up, and the water, it's going up, but just taking its good old merry time. Now, that's, of course, because of the specific heat of soil. Soil has a low specific heat, meaning you can absorb a little bit of energy and its temperature goes up pretty quickly. So as the energy is provided, it was the same lamp for both. So both were absorbing the same amount of energy. Notice that the soil's temperature went really quickly, very high, up to, it looks like 33 or 32. And then, anyway, confused. And then the water went up, but notice at the end, when it cooled off, the soil, because it heated up most quickly, it also cooled off very quickly. I mentioned that heat capacity is not only about absorbing heat, but also releasing heat. So something with a low heat capacity or low specific heat, in the case of the soil, it'll heat up very quickly and it will cool off very quickly because it doesn't take a lot of energy for it to change temperature. That's what specific heat is all about. So in conclusion, if I can jump over here, they ask, what is the difference? I kind of mentioned it already. It's all about that lower heat capacity that the soil has because it doesn't require a lot of heat energy to change its temperature. And it's true for either absorbing heat or releasing heat. So I hope this was adequate information to help you. There's some more questions that follow. If anything I said is confusing, again, I have to kind of go relatively quickly, but I apologize. If there's any loose ends, please contact your teacher. We are here to help you, and we appreciate your patience and dedication to learning chemistry. Thank you. Bye.